somewhere out there, separated from us by an ocean of empty space. There may be a civilization staring up at their own sky, wondering if anyone is staring back. And here is the strange, almost unbearable reality. Even if they exist, even if they are real, intelligent, and desperate to reach us, the universe itself may have already made their journey impossible. Not because they lack the will, not because they lack the intelligence, but because the laws of physics, the size of space, and the brutal arithmetic of energy conspire against any visitor before they ever take a single step toward Earth. This is why the most haunting question in all of science may not be whether aliens exist, but whether the cosmos was built in a way that keeps every living thing forever locked inside its own tiny corner of the dark. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. Start with the number that breaks the human mind before anything else does. The nearest star to our sun is called Proxima Centauri. It is a small, dim, red dwarf, barely a flicker compared to our own star, and it sits 4.24 light-years away from Earth. That phrase, light years, hides the horror inside it. A light year is the distance light travels in a single year, moving at the fastest speed anything in this universe is allowed to move. Light covers about 300,000 kilometers every second. In 1 second, a beam of light could circle the Earth more than 7 times. And yet, even moving that fast, light takes more than 4 years to cross the gap between us and our closest stellar neighbor. Translated into kilometers, Proxima Centauri sits roughly 40 trillion kilometers away. Write that number out and it becomes a 4 followed by 13 zeros. That is, the distance to the closest star, the nearest one, the easy one. Now consider what that means for a spacecraft built by living hands. The fastest object humanity has ever launched is the Parker Solar Probe, a small craft sent to skim the outer atmosphere of the Sun. At its peak, it reaches speeds of around 690,000 kilometers per hour. That is unimaginably fast by human standards. Nothing we have ever built has moved quicker. And yet, if you pointed the Parker Solar Probe at Proxima Centauri and let it fly in a straight line, it would take around 6,500 years to arrive. 6,500 years to reach the closest star. The pyramids of Egypt are about 4,500 years old. A journey to our nearest neighbor would last longer than all of recorded human civilization, and it would only get us to the very first stepping stone in a galaxy filled with hundreds of billions of stars. This is the wall. This is the first and most fundamental barrier standing between any alien civilization and the surface of our planet. The distances are not large. They are absurd. They are so far beyond human intuition that our brains simply refuse to hold the scale of them. And the universe does not care that we cannot picture it. The numbers remain exactly what they are. To understand just how merciless these numbers truly are, it helps to shrink the universe down to something we can almost grasp. Imagine the sun is the size of a single grain of sand placed on a table in front of you. On that same scale, the Earth would be an invisible speck of dust, drifting a few centimeters away. And Proxima Centauri, the nearest star, would be another grain of sand, not on the same table, not in the same room, but kilometers away across an empty landscape. Between those 2 grains of sand lies nothing, no other grains, no dust, just an immense, echoing emptiness that the mind struggles to even register. That is the true texture of our galaxy. Not a crowded sky packed with neighbors, but a thin scattering of lonely lights separated by gulfs of nothing so vast that the word distance begins to lose its meaning. When you look up at the night sky and see thousands of stars sprinkled across the dark, your brain plays a trick on you. it compresses them. It makes them seem close, like a handful of jewels scattered on black velvet, all within arm's reach. But they are not. Each of those points of light is a sun in its own right, and the space between them is so enormous that even light, the fastest thing that exists, takes years, decades, or centuries to cross from one to another. The night sky is not a ceiling. It is a window onto an abyss whose depth we can measure but never truly feel. And consider this scale further. Our own galaxy, the Milky Way, is a vast spiral of stars stretching about 100,000 light-years across. That means light, traveling at the ultimate speed, takes 100,000 years just to cross from one edge of our galaxy to the other. Within that spiral spin, somewhere between 100 billion and 400 billion stars, each one a sun, many of them surrounded by their own families of planets. If you tried to visit each star in our galaxy, spending just 1 second at each, it would take you thousands of years just to count them all, let alone travel between them. And the Milky Way is only one galaxy among an estimated 2 trillion galaxies in the observable universe. Each of those galaxies contains its own hundreds of billions of stars. The numbers pile up until they become meaningless, until the human mind simply gives up trying to hold them. This is the canvas on which the question of alien contact is painted. Not a cozy neighborhood of nearby worlds, but an incomprehensibly vast expanse of stars and galaxies, separated by distances so enormous that even light, the swiftest messenger in existence, takes ages to cross them. When you understand the true size of it all, the question changes. It is no longer surprising that we have not been visited. What would be surprising, what would defy all the odds, is if anyone ever could cross such an expanse at all. There is a famous thought that helps capture the loneliness of these distances. If you were standing on a planet orbiting the nearest star, and you looked back toward our sun, it would appear as just another point of light, one faint star among thousands, utterly unremarkable, with no hint that it warms a world full of life. From that distance, Earth itself would be completely invisible, lost in the glare of the sun, far too small and far too dim to be seen by any ordinary telescope. We are, from the perspective of even our nearest neighbors, a speck too small to notice, orbiting a star too ordinary to single out, in a galaxy too vast to search. That is our address in the cosmos. A grain of dust, circling a grain of sand, in a desert of unimaginable size. Most people, when they imagine alien contact, picture a sleek ship gliding effortlessly across the stars. They imagine the journey as a kind of long road trip, tedious, perhaps, but ultimately possible with enough patience and good engineering. The reality is far stranger and far more punishing. Because the problem is not just distance. The problem is energy. To move anything across space, you must accelerate it. To accelerate it, you must spend energy. And the faster you want to go, the more energy you must burn, not in a gentle, linear way, but in a way that grows monstrously as you approach the speeds you would actually need. Imagine a civilization wanted to send a single spacecraft to a nearby star within a reasonable span of time, say within a single lifetime of one of its travelers. To do that, the ship would need to travel at something like 10% of the speed of light, around 30,000 kilometers every second. At that pace, the trip to Proxima Centauri would still take more than 40 years one way. That is already a lifetime commitment. But here is where physics turns cruel. The amount of energy required to push even a modest spacecraft to 10% of light speed is staggering. For a vessel weighing as much as a large ship, the energy needed approaches the total amount of energy that all of human civilization produces in many years. Not seconds, not minutes, Years of the entire planet's power output poured into accelerating one single craft to 1/10 of the speed of light. And that is only to reach 10%. To go faster, the cost does not simply double. It explodes. The mathematics of relativity, first worked out by Albert Einstein in the early 1900s, reveals something deeply unsettling about motion itself. As an object moves faster and faster, approaching the speed of light, its effective mass increases. The closer you get to light speed, the heavier the object behaves, and the more energy it takes to push it even slightly faster. To reach the actual speed of light, the energy required would become infinite. Not very large, not impossibly large, literally infinite. This is not an engineering limit that a smarter species might overcome with a clever trick. It is built into the structure of space-time. It is woven into the fundamental rules that govern everything that exists. No matter how advanced a civilization becomes, no matter how brilliant their scientists, they cannot pour an infinite amount of energy into a finite ship. And so the speed of light stands as a cosmic ceiling, a barrier that nothing carrying mass is ever permitted to cross. This single fact reshapes the entire question of alien contact. Because if nothing can travel faster than light, then the distances between stars are not just large, they are sentences. They are travel times measured in decades, centuries, and millennia, with no shortcut available anywhere in the laws of nature as we currently understand them. A civilization that wanted to reach us could not simply decide to come. They would have to accept that the journey would outlast generations, that the travelers who left would never be the same beings who arrived, and that the energy required might exceed what their entire world could produce. The universe did not place a lock on the door between civilizations. It placed the door so far away that walking to it would consume everything you had. And to understand why this barrier is so absolute, you have to understand where it comes from. The speed of light is not just the speed at which light happens to travel. It is the maximum speed at which any information, any influence, any cause and effect can move through the fabric of reality. It is, in a sense, the speed of the universe itself. Einstein discovered that space and time are not separate and fixed, but woven together into a single fabric, and that this fabric has a built-in speed limit baked into its very geometry. When you try to push something faster and faster, you are not just fighting against resistance. You are fighting against the structure of time and space. Strange things begin to happen. For an object approaching the speed of light, time itself slows down relative to the rest of the universe. Distances ahead of it appear to contract. The faster you go, the more the universe seems to warp around you, as if reality itself is straining to keep you from breaking its most fundamental rule. These are not science fiction inventions. They have been measured, again and again, in particle accelerators where tiny particles are pushed to within a whisper of light speed, and in atomic clocks flown aboard fast aircraft, which tick ever so slightly slower than identical clocks left on the ground. The speed limit is real. It is the most thoroughly tested principle in all of physics, and it has never once been broken. Every experiment ever designed to challenge it has only confirmed it more firmly. In the great machines where scientists accelerate particles to staggering speeds, those particles approach the speed of light but never reach it, growing harder and harder to push the closer they get, exactly as Einstein's equations predict. The energy poured into them climbs higher and higher, yet the speed creeps up by smaller and smaller amounts, as though the universe itself were pushing back, refusing to let anything cross the final threshold. This is not a temporary limit awaiting a clever workaround. It is one of the deepest truths we have ever discovered about the nature of reality. as fundamental as the fact that time moves forward, or that heat flows from hot to cold. To imagine a civilization breaking this limit is to imagine them breaking the universe itself, rewriting the rules that govern everything that exists. And there is no evidence, anywhere, in any experiment or observation, that such a thing is possible. This is the foundation on which the impossibility rests. Everything else, the energy, the fuel, the time, the danger, all of it flows downstream from this single, unyielding fact. Nothing with mass can reach the speed of light, and so the stars remain forever, just out of reach. To truly feel the weight of this energy problem, it helps to think about what energy actually is and where a civilization would have to find it. Everything a civilization does, lighting its cities, powering its machines, feeding its people, requires energy. On Earth, we draw that energy from the sun, from the fuels buried in our planet, from the splitting of atoms, from the wind and the water. All of it together, every power plant and every engine on the entire planet, adds up to a certain amount of energy produced each year. Now, recall what we said earlier, that accelerating even a single modest ship to 1/10 of light speed would require many years of that entire planetary output. Pause and let that sink in. Not one city's worth of energy, not one nation's worth. The combined output of an entire world, harnessed for years, poured into a single ship, and that ship would still take more than 40 years to reach only the nearest star. To reach stars farther away, or to travel faster, the energy required climbs into realms that begin to rival the output of stars themselves. Some have imagined that a truly advanced civilization might learn to capture the entire energy output of their own star, building vast structures to surround it and harvest every ray of light produces. Such a civilization, with the power of an entire star at its command, might finally have enough energy to attempt interstellar travel on a meaningful scale. But building a structure to surround a star is itself a project of almost unimaginable difficulty, requiring more raw material than exists in many planetary systems and engineering far beyond anything we can conceive. And even with the full power of a star, the energy cost of crossing the truly vast distances of the galaxy would remain staggering. This is the relentless logic of the energy barrier. It does not yield to cleverness. It does not bend to determination. The faster you wish to go and the farther you wish to travel, the more energy you must find, and the amounts required quickly outstrip anything a civilization could plausibly gather, even at the height of its power. The universe seems to have set the price of travel deliberately, cruelly high, high enough that even the dream of reaching the nearest star demands the wealth of an entire world, and the dream of crossing the galaxy demands the wealth of stars. There is a temptation here to imagine an escape. Surely, the thinking goes, a sufficiently advanced species could simply build a faster engine. Surely there is some exotic technology, some breakthrough waiting in the future, that would let them slip past the limits that trap us today. This is where dreams meet the hard edge of what is actually allowed. Consider the most powerful rocket fuel humanity has ever used: chemical propulsion, the controlled burning of fuel that lifts our rockets off the ground. Chemical rockets are extraordinary machines, but they are pitifully weak when measured against interstellar distances. The exhaust leaves the engine at only a few kilometers per second. To reach another star within any reasonable time, you would need a fuel tank larger than entire planets, because the rocket must carry not only its payload but all the fuel needed to accelerate that fuel, and then more fuel to accelerate that, in a spiraling tower of impossibility. This is called the tyranny of the rocket equation, And it is one of the most quietly devastating truths in all of spaceflight. Every kilogram of fuel you add must itself be accelerated, which requires more fuel, which adds more mass, which requires more fuel still. The numbers climb so steeply that chemical rockets become useless for crossing interstellar space before you have even left the starting line. The problem is not that chemical rockets are weak in any ordinary sense. They are powerful enough to hurl enormous machines off the surface of a planet, to break free of a world's gravity, to send probes across our own solar system. By every standard that matters within a single star system, they are triumphs of engineering. But the gulf between the stars is so much larger than the gulf between planets that the comparison becomes almost meaningless. A rocket that can cross our solar system in a few years would take tens of thousands of years to reach even the nearest star. Because the distance is not merely greater, it is greater by an amount that defies intuition, hundreds of thousands of times farther than the span between worlds within our own system. To put it plainly, if you tried to build a chemical rocket capable of reaching the nearest star within a human lifetime, the amount of fuel it would require would outweigh the entire known universe. The equation simply collapses into absurdity. So, engineers dream of better methods. Nuclear propulsion, where the energy of splitting or fusing atoms drives the ship forward. Ion engines, which accelerate charged particles to enormous speeds. Solar sails, vast reflective sheets pushed gently by the pressure of starlight or focused beams of energy. Antimatter engines, which would convert matter into pure energy with terrifying efficiency. Each of these is real. Each has been studied seriously by scientists and engineers, and each, when examined closely, runs into the same wall. Take nuclear propulsion first. In the 1950s and 60s, scientists seriously studied a design where a spacecraft would be pushed forward by detonating a series of nuclear devices behind it, riding the shockwaves like a surfer on a wave of controlled explosions. The idea sounds insane, and in many ways it was, but the physics actually worked. A ship like that might reach a few percent of light speed. Yet, even at its most optimistic, such a vessel would still take a century or more to reach the nearest star, and the engineering challenges of containing and surviving thousands of nuclear blasts while keeping a crew alive remain far beyond anything we can build. Fusion offers a gentler dream. If we could harness the same process that powers the sun, the fusion of light atomic nuclei into heavier ones, releasing tremendous energy, we might build an engine that runs for decades, steadily pushing a ship toward the stars. But we have spent more than half a century trying to build a working fusion reactor on Earth, in a controlled laboratory, with an entire planet of resources at our disposal, and we have only recently managed to make one produce more energy than it consumes, and only for the briefest of moments. Now imagine building such a reactor that must run continuously for 40 years in the freezing radiation-soaked void between stars, with no possibility of repair, no replacement parts, and no margin for error. A single failure would doom everyone and everything aboard. The fusion reactor that powers our sun works because the sun is unimaginably massive, its own crushing gravity squeezing its core to the temperatures and pressures where fusion ignites naturally. We have no such gravity to work with. To fuse atoms here, we must recreate the conditions found in the heart of a star inside a machine small enough to fit on a planet or aboard a ship, holding a substance hotter than the sun's core in place, using fields and forces of staggering delicacy. The slightest instability, the briefest loss of control, and the reaction sputters out or damages the machine that contains it. Sustaining such a reaction for a few seconds in a laboratory has been the work of generations of brilliant scientists. Sustaining it for 40 years, in the cold and the dark, with no engineers to tend it and no replacement parts to install, is a prospect so far beyond our reach that it lives more in hope than in expectation. The ion engine is a marvel of efficiency, gently accelerating a ship over years by throwing out a thin stream of charged particles. We use ion engines today on real spacecraft, and they work beautifully for slow, patient journeys within our own solar system. But their gentle push, while efficient, is far too weak to reach the speeds needed for interstellar travel within any reasonable span of time. A solar sail pushed by a powerful laser might reach a meaningful fraction of light speed, but only for a tiny probe weighing a few grams, nothing remotely like a crude vessel carrying living beings. And even then, slowing down at the destination becomes its own nightmare, because a sail that is pushed away from a star cannot easily be pushed back to stop. Then there is antimatter, the most powerful fuel that physics allows. When matter meets antimatter, both are annihilated completely, converting their entire mass into pure energy with perfect efficiency. In theory, an antimatter engine could propel a ship to a large fraction of light speed, but here, reality intervenes with a cruel joke. Antimatter is the most expensive and difficult substance ever produced. In all the decades that scientists have been making it in particle accelerators, the total amount ever created amounts to far less than a single gram. To fuel an interstellar voyage, you would need many kilograms of it, and producing even 1 gram with our current methods would take longer than the age of the universe and consume more energy than entire nations generate. Storing it is another nightmare entirely, since antimatter annihilates instantly upon touching any ordinary matter, including the walls of whatever container you try to keep it in. This is the part that science fiction quietly ignores. Every propulsion method that looks promising on the surface dissolves the moment you examine the details. And stopping is as hard as starting. If a ship accelerates to 1/10 of light speed over the first half of its journey, it must spend the second half decelerating with equal force, or it will simply scream past its target in a blur and vanish into the dark on the far side. That doubles the energy cost. It doubles the fuel. It doubles the engineering burden of a problem that was already beyond reach. The universe does not just make it hard to leave. It makes it equally hard to arrive. There is a beautiful, terrible symmetry to it. The same physics that makes acceleration so costly makes deceleration just as costly. You cannot coast to the stars and hope to stop gently when you arrive. You must fight the universe twice, once to gain your speed and once to lose it, and both battles demand the full, impossible price. And consider one more cruel detail about all of these propulsion methods. The fuel you carry to slow down at your destination must itself be carried the entire way, which means it must be accelerated along with the ship at the start of the journey. So the fuel for stopping becomes part of the mass you must accelerate, which requires more fuel for the acceleration, which adds more mass still. The same merciless spiral that defeats the chemical rocket reappears in every scheme, no matter how exotic. You cannot escape the rocket equation. It follows you into every design, every fuel, every clever idea, demanding its price again and again. Whether you burn chemicals, split atoms, fuse hydrogen, or annihilate antimatter, the fundamental problem remains: you must carry the means of your own acceleration and deceleration with you, and every kilogram of that means demands more means to move it. The only way to truly escape this trap would be to gather fuel along the way, or to be pushed from outside rather than carrying your engine within. This is why the idea of beaming energy to a ship from its home system, using powerful lasers to push a sail, is so attractive. It leaves the engine behind, on the home world, and sends only the sail and its tiny payload into the dark. But as we have seen, this only works for the smallest of probes, and it offers no way to slow down at the far end. A laser that pushes you away from home cannot reach around to push you back to a stop at your destination. You would arrive moving at a fraction of light speed, with no way to brake, doomed to streak past your target and vanish forever into the emptiness beyond. Every path leads back to the same wall. Every clever idea, followed to its conclusion, runs into the same fundamental limits. The universe has arranged things such that there is no free ride, no shortcut, no loophole that does not demand a price too steep to pay. Now imagine, for a moment, that a civilization somehow solved all of this. Imagine they had energy to spare, engines that worked, and the patience to plan a journey lasting centuries. A new enemy rises to meet them, one that grows more dangerous the faster they go. Empty space is not truly empty. Scattered across the void between stars are atoms of hydrogen, grains of dust, tiny fragments of matter drifting in the dark. To a stationary observer, this material is so sparse that it seems irrelevant. You might find only a single atom in a cube of space, several centimeters across. But to a spacecraft moving at a significant fraction of light speed, that thin scattering of matter becomes a wall of bullets. When you are moving at 30,000 kilometers per second, even a single hydrogen atom strikes your hull with tremendous violence. A speck of dust, the size of a grain of sand, would hit with the energy of a small explosion. The faster you travel, the more energy each impact carries, and the more frequently those impacts occur. At high enough speeds, the gentle drift of interstellar gas transforms into a continuous storm of radiation and erosion, slowly grinding away at any shield the travelers might build. Think about what that means in practice. A grain of dust that you could barely see, drifting harmlessly in space, becomes a projectile carrying the punch of an artillery shell when your ship slams into it at a fraction of light speed. And there is no way to avoid these grains, because space is full of them, scattered everywhere, along any path you might choose. To survive, the ship would need armor of staggering thickness, which adds mass, which demands more fuel, which feeds back into the same impossible equation that doomed the journey in the first place. A heavily armored ship is a heavy ship, and a heavy ship requires vastly more energy to accelerate, which means more fuel, which means more mass, which means more armor needed to protect the larger vessel. Around and around it goes, every solution feeding the very problem it was meant to solve. To understand the violence of these impacts, picture standing in a gentle rain. Each drop is harmless, barely felt. Now imagine moving through that same rain at the speed of a bullet. The drops that were once soft and gentle would strike you like a hail of stones. This is what happens to a ship moving near light speed through the thin gas of interstellar space. The atoms that drift harmlessly in the void, so sparse you could travel for kilometers without meeting one, become a relentless barrage when you slam into them at such tremendous speed. At a large fraction of light speed, even individual atoms carry enough energy to damage the ship's hull, to penetrate its skin, to bombard anything inside with radiation. The forward-facing surfaces of the ship would be under constant assault, eroded grain by grain, atom by atom, across the entire span of the journey. And the larger particles, the occasional grain of dust, the rare pebble drifting in the dark, would be catastrophic. A single collision with even a small object at near light speed would release energy comparable to a powerful explosion, potentially destroying the ship outright. Across a journey of light years, the chance of encountering at least one such object becomes a serious threat. A roll of the dice repeated countless times, where a single bad outcome ends everything. There is no way to dodge these hazards. At such speeds, you would strike an object before you could even detect it and react. The only defense is armor, and armor means mass, and mass means the energy problem grows worse. And the radiation problem extends further still. Space is bathed in cosmic rays, high-energy particles that race through the galaxy at nearly the speed of light. On Earth, we are protected by our atmosphere and the planet's magnetic field, which deflect most of this radiation before it reaches the ground. We live our entire lives beneath an invisible shield, never realizing how much it protects us. A spacecraft crossing the interstellar void has no such shield. Its occupants, whether they are biological beings or delicate machines, would be exposed to a constant rain of radiation for the entire duration of the trip. Over years and decades, this radiation damages cells, corrupts electronics, and degrades every material it touches. Any living crew would face an environment that slowly tears their bodies apart at the molecular level. The genetic material inside every cell would be struck again and again by high-energy particles, accumulating damage faster than any body could repair it. Any robotic crew would watch their circuits accumulate damage until systems began to fail, bit by bit, until the ship became a dead hulk drifting silently through the dark. The longer the journey, the worse it becomes. And the journeys, as we have seen, are measured in lifetimes. So even a civilization with limitless energy faces a gauntlet of physical threats, impacts, radiation, erosion, and the slow decay of everything they bring with them. The void is not a peaceful highway waiting to be crossed. It is a hostile expanse that actively works to destroy anything foolish enough to enter it at speed. Every kilometer of the journey is a small battle against the indifferent violence of space itself. And here a strange and beautiful complication enters the story. One that at first seems like it might offer hope, but which reveals its own form of cruelty upon closer inspection. We spoke earlier of how time slows down for an object moving close to the speed of light. This effect, called time dilation, is one of the most astonishing consequences of Einstein's discoveries, and it has been confirmed countless times in experiments. For travelers moving at a large fraction of light speed, time aboard their ship would pass more slowly than time back home. A journey that takes 400 years as measured from Earth might feel like only a few decades, or even a few years, to the travelers themselves, if they could travel fast enough. In principle, this means a single crew might survive a journey that would otherwise require many generations, because for them, far less time would pass. At first glance, this seems like a way out. If you could only travel fast enough, you could compress a centuries-long journey into a single lifetime, experienced from inside the ship. But the catch is brutal, and it brings us right back to where we started. To experience significant time dilation, you must travel at a very large fraction of light speed, far faster than the 10% we discussed earlier. And as we have seen, the energy required to reach such speeds grows without bound as you approach the speed of light. To slow time meaningfully for the travelers, you would need so much energy that the journey becomes more impossible, not less. The faster you go, the more time you save, but the more energy you must spend, and the energy cost rises far faster than the time savings. There is also a deeper sorrow hidden in time dilation. Even if travelers could compress their journey into a few short years of their own experience, the universe back home would not wait for them. By the time they arrived at their destination, centuries would have passed in the wider universe. If they ever tried to return, they would come back to a world utterly transformed, where everyone they once knew was long gone, where their civilization had risen, fallen, or changed beyond recognition. They would be travelers not just across space, but across time. Exiles who could go forward into the future but never back, cut off forever from the world they left behind. Time dilation does not break the barriers between worlds. It simply trades one kind of separation for another, replacing the loneliness of distance with the loneliness of time. Let the human element enter the picture, because this is where the impossibility becomes almost poetic. Suppose the journey takes 400 years. That is not an unreasonable estimate for many realistic interstellar voyages, even with advanced technology. 400 years is far longer than any individual living thing we know of can survive. The beings who board the ship at the start would never see the destination. Their children would not see it. Their children's children would not see it. Generation after generation would be born, live their entire lives, and pass on inside a metal vessel drifting through absolute darkness, never knowing the world they came from, never reaching the world they were sent toward. This is the idea of a generation ship, a vessel designed to carry a small population across the centuries, with descendants completing the journey their ancestors began. It sounds romantic until you examine what it actually requires. A closed ecosystem that must function flawlessly for hundreds of years, recycling every breath of air, every drop of water, every scrap of food, without a single catastrophic failure. Think about that requirement. On Earth, we have an entire planet to absorb our mistakes, oceans to clean our water, forests to refresh our air, a vast biosphere that has balanced itself over billions of years. A generation ship would have to replicate all of that in a sealed container and keep it running perfectly, for centuries, with no outside help and no room for error. A single broken air recycler, a single failed crop, a single collapse in the delicate web of life support, and everyone aboard would be lost. A society that must maintain its knowledge, its purpose, and its psychological stability across dozens of generations, despite being sealed inside a confined space with no escape and no fresh input from the outside world. History on Earth shows us how quickly human societies fracture, how knowledge is lost, how purpose erodes across mere centuries, even with an entire planet to live on. Empires rise and fall. Languages are forgotten. Skills that took generations to develop vanish in a single lifetime when the people who held them are gone. Now compress all of that fragility into a sealed can hurtling through the void, where a single breakdown in the air system or a single collapse of social order would end everyone aboard. The challenge is not only technological, it is biological, psychological, and almost spiritual. How do you ask beings to dedicate their entire existence to a goal they will never witness? For the benefit of strangers not yet born, based on a decision made by ancestors they never met. Imagine being born inside that ship. You would know no sky, no wind, no horizon. The walls around you would be the only world you had ever known, and the stars outside would be cold, distant lights that mean nothing to your daily life. You would be told that long ago, beings you never met chose this path, and that long after you are gone, beings not yet born will finally arrive. You are simply a link in a chain, a single generation in the middle of a journey with no beginning you remember, and no end you will see. What would that do to the spirit of a living thing? What kind of culture would emerge from a population that has never seen the sky, never felt rain, never stood on solid ground? Consider how strange the very concept of the destination would become to such people. To the first generation, the goal would be vivid and real. They would remember the world they left, and they would carry the dream of the world they were traveling toward. But to the 10th generation, born and raised entirely inside the ship, the destination would be little more than a legend, a story told by elders about a place no living person had ever seen. Would they still believe in it? Would they still care? Some among them might come to see the ship itself as the entire world, the only reality that matters, and might question why they should sacrifice anything for a distant goal they cannot see and may never reach. Others might lose faith, might decide that the mission their distant ancestors began was not theirs to carry. The social fabric of such a community would be under constant strain, stretched across centuries, with no way to relieve the pressure and no escape from one another. Disagreements that on Earth might be resolved by simply moving away would, aboard a ship, fester in the close confinement of a sealed world. A single generation that lost the knowledge of how to maintain the ship's systems could doom it. A single breakdown of cooperation, a single descent into conflict, in a fragile vessel where everyone depends utterly on everyone else, could end everything. History gives us no example of any human institution surviving intact across the spans of time such a journey would require. Governments fall, beliefs transform. The very languages people speak drift and change until the words of the ancestors become unintelligible to their descendants. To imagine a community holding together, with purpose and competence intact, across centuries of confinement in a metal shell, is to imagine something that has never once happened in all of recorded history. And yet that is precisely what a generation ship would demand, not just once, but flawlessly, for the entire duration of an impossible voyage. The mechanical challenges of interstellar travel are immense, but the human challenges may be even greater. A machine can, in principle, be built to last. A society of living, feeling, fallible beings, sealed away from everything they evolved to need, across more time than any culture has ever endured. That may be the most fragile component of all. And there are subtler threats too. A small, isolated population faces genetic problems over many generations. Without enough diversity, harmful traits accumulate, and the health of the descendants declines. Maintaining a genetically viable population across centuries would require careful planning and a starting group large enough to avoid these dangers, which means a larger ship, more mass, more fuel, and once again the same brutal equation rises up to block the path. Every solution creates a new problem. Every door that opens reveals another wall behind it. Some have imagined a way around the generation ship problem. What if, instead of letting generations live and pass aboard the ship, you simply put the travelers to sleep? The idea of suspended animation, freezing or slowing the body so that a traveler could sleep through the centuries and wake at the destination, is a staple of science fiction. But the reality is brutal. We have no way to safely freeze a complex living body and revive it unharmed. The very process of freezing destroys cells as ice crystals tear apart the delicate structures that keep a body alive. Even if a way were found, keeping a body in such a state for centuries, with no failure of the machinery that maintains it, presents the same impossible reliability problem as everything else. A frozen sleeper is utterly helpless, depending entirely on machines that must run flawlessly for hundreds of years. One power failure, one mechanical breakdown, and the sleepers would never wake. This is the pattern that repeats at every level of the interstellar challenge. There is no single barrier that, once overcome, lets everything else fall into place. Instead, there is a layered fortress of obstacles, each reinforcing the others, each demanding resources that the previous obstacle has already consumed. There is another possibility worth confronting, one that troubles even the most hopeful scientists. Perhaps the reason no one has reached us is not that they cannot travel, but that they are not there at all, at least not at the same time as us. Consider the timeline of our own galaxy. The Milky Way is around 13 billion years old. Earth is roughly 4.5 billion years old. Our species, in any recognizable form, has existed for only a few 100,000 years, and our technology capable of sending signals into space has existed for barely a century. In the vast sweep of cosmic time, our window of technological existence is a single flicker, gone almost as soon as it appears. Stretch the entire history of the universe across a single year, with the Big Bang on the 1st of January, and this very moment at the stroke of midnight on the 31st of December. On that scale, all of recorded human history, every empire, every war, every discovery, every life that has ever been written down, would fit into the final few seconds before midnight. Our technological age, the brief span in which we could send a signal to the stars, would be less than the final fraction of the last second. That is how thin our slice of time truly is. If alien civilizations follow a similar pattern, rising, flourishing for a brief moment, and then fading, then the galaxy might be filled with the silent ruins of species that came and went, each separated from the others not only by distance but by time. Two civilizations might both exist within reach of one another in space, yet be separated by millions of years. One might rise and fall long before the other ever learns to look at the stars. They would be like two ships passing in an endless night, each unaware that the other had ever sailed. Imagine a civilization that blossomed 1 billion years ago, reached toward the heavens, and then vanished, leaving nothing behind but cooling ruins on a forgotten world. Their light, their signals, their dreams, all of it would have faded into silence long before the first single-celled life appeared in Earth's oceans. And by the time we learned to listen, there would be nothing left to hear. The problem of timing cuts deeper than most people realize. Even if a civilization arose, thrived, and reached for the stars, the span of time during which it could make contact with another civilization might be extraordinarily brief. A civilization must survive long enough to develop the technology for contact, but not so long that it is already faded by the time another civilization arises. Two civilizations would have to overlap, their windows of capability aligning across the vast sweep of cosmic time, and they would have to overlap closely enough that, given the immense delays of communication and travel, contact could actually occur. When you consider how brief these windows might be, measured against the billions of years of cosmic history, the chance of two of them aligning begins to seem almost impossibly small. It is like trying to have two candles lit at random moments across thousands of years, both burning at the same instant in the same small room. Most candles would burn and gutter out long before another was ever lit. The cosmos may be a vast hall filled with candles that flickered to life and faded, one after another, across the ages. Each one a civilization, each one briefly bright, and almost none of them ever burning at the same time as another. We might be one such candle, burning now, in a hall where most of the others have already gone dark, and where those not yet lit will only flicker into being long after we ourselves have faded. This is perhaps the most melancholy possibility of all. Not that the universe is empty, not even that the distances are too great, but that life and intelligence are scattered so thinly across time that no two sparks ever meet, each one rising and falling alone, never knowing that others came before or will come after. The silence of the stars may be the silence of a hall full of candles that never share their light. This is part of what scientists call the Fermi paradox, named after the physicist Enrico Fermi, who famously asked a simple question: if the universe is so vast and so old, where is everybody? If intelligent life is common, the galaxy should be teeming with it, and some trace of it should have reached us by now. Yet we see nothing. No signals. No probes. No unambiguous sign of any other mind among the stars. The silence is deafening. For decades, scientists have pointed enormous radio telescopes at the sky, listening patiently for any artificial signal, any whisper of intelligence from beyond. They have scanned thousands of stars, sweeping across vast ranges of frequencies, searching for the faintest hint that we are not alone. And the result, so far, has been silence. A profound, unbroken silence that stretches across the entire sky. The distances we have discussed offer one of the most compelling explanations for that silence. Perhaps the galaxy is not empty. Perhaps it is full of life, full of thought, full of beings who dream of the stars exactly as we do. But each of them is trapped, just as we are, behind the same walls of distance, energy, time, and physics. Perhaps every civilization that has ever existed has stood at the edge of the cosmic ocean, looked out at the impossible gulf, and realized that it cannot be crossed. If that is true, then the universe is not silent because it is empty. It is silent because the laws of nature have quarantined every living thing inside its own solar system, unable to reach across the void to anyone else. The loneliness would not be an accident. It would be a feature of reality itself. And there is something even more chilling buried in this thought. If the barriers are truly as severe as the physics suggests, then it would not matter how many civilizations exist. The galaxy could contain 1,000,000 thriving worlds, each filled with curious, brilliant, longing minds, and still none of them would ever meet. Each would remain forever isolated, separated from all the others by an emptiness that no amount of intelligence or determination could overcome. A galaxy crowded with life could still feel utterly, absolutely alone. There is an even darker thought lurking behind the silence of the stars, one that some scientists have wrestled with for decades. It is the idea of the Great Filter. The reasoning goes like this. For a civilization to reach out across the stars, an enormous chain of events must all go right. Life must first arise from non-living matter, itself a step we do not fully understand and have never witnessed beginning anywhere but Earth. That simple life must then evolve into complex life, which on Earth took billions of years and may have depended on chance events that rarely occur. Complex life must then give rise to intelligence, which is far from guaranteed. Life thrived on Earth for hundreds of millions of years without producing a single technological species. That intelligence must then develop technology, survive its own dangers, and last long enough to attempt contact with the stars. At each of these steps, something could go wrong. At each step, the chain could break. The Great Filter is the name for whatever step, or steps, are so difficult that almost nothing makes it through. And here is the unsettling part. We do not know where the filter lies. It might lie behind us, meaning that the rise of intelligent, technological life is so improbable that we are among the very few, perhaps the only ones, to have made it this far. If that is the case, then the silence of the stars is explained by our rarity. We are alone not because contact is impossible, but because there is almost no one else out there. But the filter might lie ahead of us. It might be that civilizations regularly arise, only to fade before they can reach the stars, undone by their own technology, by the collapse of their worlds, by some danger we have not yet encountered. If the filter lies in our future, then the silence is a warning, a sign that something tends to stop civilizations before they can spread, and that we too may face that obstacle in the time to come. Either way, the Great Filter offers a haunting explanation for why the heavens are so quiet. Combined with the physical barriers of distance, energy, and time, it paints a picture of a universe in which the emergence of a star-faring civilization is so improbable and the obstacles so severe that contact between worlds may be among the rarest events the cosmos ever produces, if it produces them at all. The silence may be telling us something profound about how hard it is, not just to travel between the stars, but to even become the kind of being that would want to try. But let us not surrender too quickly, because the human imagination has never accepted a wall without searching for a way around it. If you cannot travel faster than light through space, perhaps you could find a way to bend space itself. This is where the most exotic ideas in physics enter the conversation. Ideas that live at the very boundary of what equations permit and what reality might forbid. One such idea is the wormhole. In the mathematics of Einstein's theory of gravity, space and time are not a fixed stage but a flexible fabric that can stretch, curve, and warp in the presence of mass and energy. In principle, this fabric could be folded so dramatically that two distant points are connected by a shortcut, a tunnel through the structure of reality itself. Picture a sheet of paper with two dots drawn at opposite ends. Normally, to travel from one dot to the other, you must cross the entire length of the paper. But if you fold the paper so the two dots touch, you could punch through and cross the distance in an instant. The genius of the idea is that it does not require you to move faster than light through space at all. Instead, it shortens the space itself, bringing two distant points together so that the gap you must cross becomes almost nothing. In principle, this would let you sidestep the speed limit entirely, arriving at a distant star without ever having traveled quickly through the space in between. A wormhole is the cosmic version of that fold. A tunnel that connects two far-apart regions of space, allowing a traveler to step in near Earth and step out beside a distant star, having crossed light years in a moment. It is a beautiful idea. It appears in the equations as a genuine mathematical possibility. But the conditions required to create and hold open such a tunnel are staggering. First, you would have to create the wormhole at all, and we have no idea how to do that. Bending space dramatically enough to punch a tunnel through it would require concentrating energy and mass in ways that may be physically impossible, perhaps approaching the conditions found inside a black hole. And a natural wormhole, even if one existed somewhere in the universe, would not be a gentle doorway. The forces near it would be so extreme that anything approaching would likely be torn apart long before it could pass through. Then, even if you somehow created one, you would face the problem of keeping it open. To keep a wormhole from collapsing the moment it forms, you would need a substance with negative energy, a kind of exotic matter that pushes outward in a way ordinary matter never does. Every form of matter we have ever encountered has positive energy and creates attractive gravity. The exotic matter required to prop open a wormhole would have to do the opposite, generating a kind of repulsive influence that holds the tunnel apart against its own tendency to slam shut. We have never found this exotic matter in any meaningful quantity. We have glimpsed hints of something vaguely similar in tiny quantum effects in laboratories, but nothing remotely like the vast amounts that would be needed. We do not know if it can exist in the amounts required. And even if it could, the engineering of stabilizing a hole in space-time large enough for a ship to pass through, without it tearing apart or releasing catastrophic energy, lies so far beyond anything we can imagine that it may as well be a fantasy. A wormhole large enough for a ship would require an amount of exotic matter so vast that some calculations suggest you might need more than exists in entire regions of space. And again, we are not even certain such matter exists at all. Another idea is the warp drive, a concept where, instead of moving through space, you move space itself. The notion is that a ship could sit inside a bubble of flat space, while the space in front of the bubble contracts and the space behind it expands. The bubble, carrying the ship, would be pushed along faster than light, without the ship ever locally exceeding light speed, neatly sidestepping Einstein's rule. This idea, worked out in detail by a physicist in the 1990s, is elegant on paper. The ship inside the bubble would feel no acceleration, no crushing forces, no sense of motion at all. It would simply ride along as the universe rearranged itself around it. But like the wormhole, it demands enormous quantities of negative energy, quantities that may simply not exist in our universe. Some early estimates suggested the energy required would exceed the total energy content of entire stars, or even larger amounts still. More energy than exists in everything we can see. Later refinements brought the numbers down considerably, and clever variations on the original design reduced the requirements further, but never to anything remotely achievable, and never with any guarantee that the exotic ingredients required are physically possible at all. There are also deeper problems hiding in these ideas. Some physicists have shown that wormholes and warp drives, if they could exist, might allow not just travel across space but travel backward through time, opening the door to paradoxes that seem to violate the basic logic of cause and effect. Many physicists take this as a hint from nature, a sign that the universe simply does not permit such things, and that the apparent loopholes in the equations are closed by deeper laws we are only beginning to understand. It is worth dwelling on this point, because it reveals something important about the relationship between mathematics and reality. The equations of physics describe what is possible within their own framework, but they do not guarantee that everything they permit can actually exist. There are many solutions to the equations of physics that describe situations that never occur in nature, mathematical possibilities that reality simply does not realize. Wormholes and warp drives may well belong to this category. They are consistent with the equations, in the sense that you can write them down without contradiction, but the universe may have additional rules, not yet fully understood, that forbid them from ever forming, just as the universe forbids many other things that the bare equations would seem to allow. The history of physics is full of examples where a mathematical solution was discovered, celebrated as a possibility, and then shown to require conditions so extreme or so unnatural that it could never actually happen. Exotic matter with negative energy in the quantities required, stable tunnels through space-time, bubbles of contracting and expanding space. All of these may be mathematical mirages, beautiful on paper but forever beyond the reach of physical reality. And even if, against all odds, one of these methods could exist, the gulf between a mathematical possibility and a working technology is itself almost unimaginably vast. We can write down the equation for a warp drive, but we have not the faintest idea how to build one, what it would be made of, how it would be controlled, or how a civilization could ever gather the resources it would demand. A blueprint that exists only as a line in an equation is not a vehicle. It is a dream wearing the clothing of science. These ideas are not lies. They are honest explorations of what the equations allow. But there is a vast difference between something being mathematically permitted and something being physically achievable. A blueprint that requires materials which may not exist, in quantities that may not be possible, controlled by technologies we cannot even sketch, is not a path forward. It is a reminder of just how high the walls truly are. And here is the sobering thought that ties it all together. If even the most advanced theoretical loopholes require resources beyond entire stars, then crossing interstellar space is not merely difficult. It is the kind of task that strains the very limits of what reality permits any being to do. At this point, someone always raises an objection. What about all the reports? For generations, people have claimed to see strange lights in the sky, unexplained craft, objects moving in ways that seem to defy known physics. Surely, the thinking goes, Some of these must be visitors from other worlds, evidence that the barriers we have described can be crossed after all. It is worth addressing this honestly, because it speaks directly to the heart of the question. The overwhelming majority of these sightings, when carefully investigated, turn out to have ordinary explanations. Aircraft seen from unusual angles, weather phenomena, reflections, optical illusions, distant lights misjudged in size and distance. The planet Venus, blazing bright near the horizon, has been reported as a mysterious craft more times than anyone can count. Our minds are pattern-seeking machines, prone to seeing intention and design where there is only coincidence, especially when we are primed to expect the extraordinary. A small number of sightings remain genuinely unexplained, but unexplained does not mean alien. It simply means we lack enough information to identify what was seen. Throughout history, countless phenomena were once mysterious and later understood through patient investigation. An unexplained light in the sky is a puzzle, not proof of a craft that has crossed light years of impossible distance. And here is the crucial point. The physical barriers we have spent this entire journey exploring are not minor obstacles that a clever civilization might quietly slip past. They are woven into the deepest laws of the universe: the speed of light, the cost of energy, the violence of high-speed travel, the vastness of the distances. For any of the visitation claims to be true, a civilization would have to have overcome every single one of those barriers, crossing an impossible gulf, expending the energy of worlds or stars, surviving a journey of lifetimes, all to arrive here and do nothing more than flash some lights and vanish. It does not add up. A civilization capable of crossing interstellar space, of solving the most difficult problem any beings could ever face, would announce itself in ways that left no doubt, ways far beyond ambiguous lights glimpsed at the edge of vision. The extraordinary difficulty of the journey is itself the strongest argument against the idea that we are being casually visited. The very barriers that make contact so unlikely also make it deeply improbable that fleeting, unexplained sightings represent travelers who have somehow overcome the impossible. The truth is almost certainly stranger and lonelier than the stories. We are not being visited. We are alone with our questions, gazing up at a sky that holds no secret craft, only the cold, distant fires of stars we can never reach. Perhaps, some have suggested, the answer is not to send living beings at all. Perhaps a civilization would simply build machines, small, self-contained probes that could cross the void, repair themselves, and even reproduce when they arrive at a new star system. This is the idea of the self-replicating probe, sometimes imagined as a way for a single civilization to explore the entire galaxy over millions of years. Send out one probe. It travels to a nearby star, builds copies of itself from the raw materials it finds there, and sends those copies onward to the next stars. Each new probe does the same. In this way, even at speeds far below light speed, a wave of machines could spread across the entire galaxy in a few million years, a blink of an eye in cosmic terms. It is a clever idea, and it sidesteps many of the problems that plague crewed missions. A machine does not need air, food, or water. It does not grow lonely or lose its sense of purpose. It does not age in the way living things do. And if built well, it might repair the damage that radiation and impacts inflict along the way. But even this approach runs into formidable barriers. Building a machine that can survive a journey of centuries, then mine raw materials, refine them, and construct a perfect copy of itself, all without any human guidance, requires a level of technology so advanced that we can barely imagine it. Such a machine would need to be a complete, self-sufficient factory, a miner, an engineer, and a navigator all in one, capable of operating flawlessly in an alien star system it has never seen before. And there is a darker side to the idea. A self-replicating machine that makes copies of itself, generation after generation, would be subject to errors. Just as living things mutate over generations, a self-replicating probe might accumulate flaws in its design, drifting away from its original purpose, perhaps even turning destructive. A civilization might hesitate to release such a thing into the galaxy, knowing it could not be recalled and might evolve in ways its creators never intended. And here lies one of the strangest twists in the entire puzzle. If self-replicating probes are possible, and if even one civilization in the long history of the galaxy had built them, then the galaxy should already be full of them. They should have reached every star, including ours, long ago. We should see them in our own solar system. Yet we do not. This absence is itself a kind of clue. It suggests that either no civilization has ever attempted such a thing, or that the barriers to building such machines are even greater than we imagine, or that something prevents them from spreading. Perhaps the same wall of distance, energy, and time that stops everything else. The silence of the machines is as deep as the silence of the living. And there is a further reason to doubt that even machines could bridge the gap. A self-replicating probe, for all its theoretical advantages, would still have to survive the same hostile journey as any other craft. It would still be battered by radiation and high-speed impacts across centuries of travel. Its delicate components, its computers, its sensors, its tools would still degrade in the unforgiving environment of interstellar space, where there is no one to repair them and no spare parts to install. A machine sophisticated enough to repair itself perfectly, indefinitely, across centuries, while also mining and manufacturing and reproducing, would be a marvel beyond anything we can currently build. We struggle to make machines that last a few decades here on Earth, in gentle conditions, with constant maintenance. The idea of a machine that maintains itself flawlessly through an interstellar voyage and arrives ready to build a perfect copy of itself stretches the imagination to its limit. And even if such a machine could be built, there remains the question of purpose. Why would a civilization pour the enormous resources required to build the first such probe into a project whose results they would never see, whose copies would spread across the galaxy long after their own civilization had faded? The first probe alone might consume a significant fraction of a civilization's resources, and the payoff would lie thousands or millions of years in the future, benefiting no one alive at the time of its launch. It is the same problem that haunts the generation ship, the immense cost paid now for a reward that arrives unimaginably far in the future, to recipients who do not yet exist. Perhaps this is why the galaxy is silent. Perhaps the machines, like the ships and the signals, simply cost too much and promise too little to ever be built in earnest. Perhaps every civilization that has ever contemplated the stars has run the same brutal calculation we are running now, and arrived at the same conclusion, that the price of reaching out is simply too high, and the void too vast, for the journey to ever be worth attempting. There is yet another reason the journey may be impossible, one rooted not in the difficulty of building ships, but in the expanding nature of the cosmos itself. The universe is not static. It is growing. Ever since the beginning, around 13.8 billion years ago, space itself has been stretching, carrying galaxies away from one another, like dots painted on the surface of an inflating balloon. Imagine that balloon, with dots scattered across its surface. As you blow it up, every dot moves away from every other dot. Not because the dots are moving across the rubber, but because the rubber itself is stretching between them. That is what is happening to the universe. The galaxies are not flying through space so much as being carried apart by the expansion of space itself. And this expansion is accelerating, driven by a mysterious influence that scientists call dark energy, a force that pushes the cosmos apart faster and faster as time goes on. We do not fully understand what dark energy is. We only know that it makes up most of the energy in the universe, and that its effect is to drive the great cosmic expansion ever faster. For the nearest stars within our own galaxy, this expansion is not a problem. Within a galaxy, gravity holds everything together against the cosmic stretching. Our galaxy will not be torn apart by the expansion, because the gravity binding its stars together is far stronger than the gentle push of dark energy over such relatively small distances. But between galaxies, the story changes completely. Distant galaxies are not merely far away. They are receding from us, and the most distant ones are receding so quickly that no signal, no ship, no beam of light could ever catch up to them. There exists a boundary, a cosmic horizon, beyond which galaxies are being carried away faster than light can travel toward us. This does not violate the speed limit, because it is space itself that is expanding, not the galaxies moving through space. Objects can be carried apart by expanding space faster than light, even though nothing is actually moving through space faster than light. But the consequence is final. Anything beyond that horizon is forever unreachable, not difficult to reach, not expensive to reach, permanently, eternally beyond reach, no matter how much time passes or how advanced any civilization becomes. This means that even if a thriving alien civilization existed in a distant galaxy, and even if they had mastered every technology imaginable, the expansion of the universe itself would prevent them from ever crossing the gulf to us. The cosmos is, in a very literal sense, pulling its inhabitants apart faster than they could ever hope to come together. And as the universe continues to expand, this isolation deepens. Far in the future, the galaxies we can currently see will slip beyond the horizon one by one, until a civilization living then would look up and see only their own galaxy, surrounded by an apparently empty void, with no evidence that anything else had ever existed at all. Think of how strange that future is. A civilization born many billions of years from now would have no way of knowing that the universe was ever filled with countless galaxies. The evidence would have vanished beyond their horizon. They might conclude that their single galaxy was the whole of creation, an island floating alone in an infinite emptiness, never suspecting the grand cosmos that once surrounded them. We are fortunate, in a way, to live now, in an era when the universe is still young enough that other galaxies remain visible. But even now, the door is swinging shut, and the laws of physics are turning the key. The window for any kind of contact across cosmic distances is not just narrow, it is closing. To grasp how profound this is, consider that even light itself, the fastest thing in existence, the very messenger we rely on to see the distant universe, is losing the race against the expansion. There are galaxies whose light is still reaching us now, light that began its journey billions of years ago, but which will eventually fade from view as the space between us and them stretches ever wider. Those galaxies are not moving away through space at impossible speeds. The space itself, between us and them, is growing, adding distance faster than light can cross it. It is as though you were walking toward a destination on a road that was being stretched beneath your feet, the far end receding faster than you could ever walk, no matter how fast you moved. For the most distant galaxies, the road is being stretched faster than light can travel, and so they are already, in the truest sense, beyond all possible reach. We can still see some of them, because their ancient light is still arriving. But we could never go there. We could never send anything there. And in time, Even their light will fail to reach us, as the expansion finally wins and carries them entirely beyond our horizon. This means that the universe contains regions, vast, countless regions, filled with galaxies and perhaps with life, that are utterly and permanently cut off from us, not by any technological limitation, but by the fundamental geometry of an expanding cosmos. Whatever exists out there, whatever beings might gaze up at their own skies in those distant reaches, we will never reach them, and they will never reach us. The expansion has already drawn an uncrossable line between us, and that line grows longer with every passing moment. It is one of the loneliest facts in all of science, that the universe is actively, relentlessly separating its inhabitants, sweeping them apart faster than any of them could ever hope to come together, sealing each one into an ever-shrinking island of reachable space. Let us pause and consider what it would actually take to overcome all of this at once. To reach Earth from another star, an alien civilization would need to do everything we have described, simultaneously and flawlessly. They would need to generate energy on a scale that dwarfs the output of entire worlds, perhaps entire stars, and channel it into accelerating a ship to a meaningful fraction of light speed. They would need to build an engine that has never failed in any of our wildest dreams, a fusion reactor or antimatter drive that runs for decades or centuries without a single breakdown. In the most hostile environment imaginable, they would need to shield that ship against a relentless storm of radiation and high-speed impacts, with armor thick enough to survive the journey, yet light enough not to make the energy problem even worse. They would need to keep something alive aboard, whether biological beings across countless generations, or machines sophisticated enough to maintain themselves and reproduce in an alien system. They would need to decelerate at the end, spending as much energy to stop as they spent to start, arriving gently rather than vaporizing on impact. And they would need to do all of this for a destination that, when they set out, they could see only as it was years, decades, or centuries in the past, aiming not at where Earth is, but at where Earth will be when they finally arrive, across an ocean of uncertainty. Any one of these challenges, taken alone, would test the limits of what is possible. Stacked together, they form a problem of such overwhelming difficulty that it is hard to see how any civilization, no matter how advanced, could solve all of them at once. This is the heart of the impossibility. It is not a single locked door. It is door after door after door, each one requiring everything the previous door consumed, each one demanding resources and reliability beyond anything reality seems willing to permit. And even if a civilization somehow managed all of it, they would face one final, deflating question. Why? Why pour the entire output of your world into a journey that will outlast your civilization, to reach a planet you have only glimpsed across the void, with no certainty of what you will find when you arrive? The cost would be so immense, the reward so uncertain, and the timeline so vast that even a civilization capable of the feat might simply choose not to attempt it. Think about the decisions such a civilization would have to make. They would be choosing to pour the wealth of their entire world, perhaps the wealth of their entire star, into a single project that would not bear fruit for centuries, that might fail at any of 1,000 points along the way, and that would deliver its reward, if at all, to descendants so distant they would be as strangers. No individual would live to see the outcome. No leader who authorized the mission would witness its arrival. The entire endeavor would be an act of pure faith in a future they could never share. And against this enormous, uncertain cost, what would they gain? Knowledge of another world, perhaps. The chance to spread their kind to a new star. But these rewards, however noble, are abstract and distant, while the costs are immediate and crushing. A civilization facing such a choice might well decide that its resources are better spent at home, improving the world it already has, rather than gambling everything on a journey into the impossible. This is perhaps the quietest barrier of all, and in some ways the most decisive. It is not a law of physics. It is a matter of will, of priorities, of the simple calculation that the price is too high and the reward too remote. Even if everything else could somehow be overcome, this final barrier might stop the journey before it ever began, not because it could not be done, but because no sane civilization would ever choose to do it. And if that is true for every civilization that has ever pondered the stars, then it is no wonder the heavens are silent. It is not that no one can come, it is that no one would. The stars may be unreachable not only because the physics forbids it, but because no rational being would ever pay the price the physics demands. There is a comparison people often reach for when they think about interstellar travel. They look back at the great voyages of exploration in human history, the crossing of vast oceans, the discovery of new continents, the spread of explorers across the entire surface of our world. If our ancestors could cross oceans they had never seen, in fragile wooden vessels, with no certainty of what lay beyond the horizon, surely, the thinking goes, a future civilization could cross the ocean of space in the same spirit of courage and discovery. It is a stirring comparison, but it falls apart the moment you examine the numbers. When an explorer sets sail across an ocean on Earth, the journey might take weeks or months. The destination, though unknown, lay at the end of a crossing measured in thousands of kilometers, a vast distance by human standards, but one that a determined crew could endure within a single voyage, within a single lifetime, often within a single season. The ocean, for all its dangers, could be crossed. There was air to breathe the entire way. There was the possibility of finding land, of resupplying, of turning back if things went wrong. And the rewards, new lands, new resources, new connections, were tangible and could be claimed within the lifetime of those who set out. Interstellar travel shares almost none of these features. The distances are not thousands of kilometers, but trillions, and then trillions of trillions. The journey is measured not in months, but in centuries or millennia. There is no air to breathe, no land to find along the way, no possibility of resupply, no turning back once you have committed your civilization's resources to the attempt. And the reward, if it ever comes, arrives so far in the future that no one who launched the mission could ever hope to see it. The comparison to ocean exploration fails because the scales are not merely different, they are different in kind. Crossing an ocean is a challenge of courage and skill. Crossing the gulf between stars is a challenge against the fundamental structure of reality itself, against the speed of light, against the cost of energy, against the violence of space, against the passage of deep time. No amount of courage can overcome a physical law. No amount of skill can conjure energy that does not exist. The explorers of old faced an unknown, but a reachable unknown. What lies between the stars is not merely unknown. It is, by every measure we can apply, unreachable. This is the hard truth that the romantic comparison hides. We are not standing on the shore of an ocean waiting for braver sailors. We are standing at the edge of a gulf that the laws of nature have made too wide, too costly, and too cruel for any vessel ever to cross. Let us turn now to the question of communication, because some might argue that physical travel is beside the point. Why send a ship at all when you could simply send a message? A radio signal or a beam of light travels at the maximum speed the universe allows. It carries no fuel, suffers no fatal impacts, and requires no crew to maintain across the centuries. Surely, if contact is possible at all, it would happen through communication rather than travel. This is true, in a sense, and it is the basis for nearly all of humanity's actual efforts to detect alien life. we do not expect to be visited. We hope, instead, to overhear a signal or to catch the faint glow of some distant civilization's technology. But even communication runs headlong into the same brutal walls of distance and time. Suppose a civilization around the nearest star decided to send us a message right now. That message, traveling at the speed of light, would take more than 4 years to reach us. If we replied immediately, our answer would take another 4 years to return to them. A single exchange, hello and hello back, would consume nearly a decade, and that is for the very nearest star. Most stars in our galaxy are not 4 light-years away. They are hundreds, thousands, even tens of thousands of light-years distant. A conversation with a civilization on the far side of the Milky Way would take longer than 100,000 years for a single round trip, far longer than our entire species has existed. You could send a question, and your descendants, 1,000 generations later, might receive the answer, long after everyone who asked it had been forgotten. Imagine the patience such a conversation would demand. A civilization would have to commit to a dialogue lasting longer than their entire recorded history, with each sentence separated from the next by spans of time that dwarf the rise and fall of empires. A single misunderstanding could not be cleared up in a moment. It would take centuries to even discover that a misunderstanding had occurred, and centuries more to correct it. By then, the language itself might have changed beyond recognition, the very meaning of the words drifting as generation gave way to generation on both ends of the exchange. The participants in such a conversation would not be individuals but entire chains of civilizations, each inheriting a fragment of a dialogue begun by ancestors they never knew, addressed to strangers they would never meet. This is not a conversation. It is a message in a bottle, cast into an ocean so vast that any reply would arrive in an age you cannot imagine, to people who may not remember you ever lived. And there is a deeper problem still. For 2 civilizations to exchange even a single message, they must both exist and both be listening at the same moment in cosmic time, accounting for the immense delay between them. If a civilization 1,000 light-years away sent us a signal, we would only receive it 1,000 years after they sent it. By the time it reaches us, they may have faded into silence, their world long since gone quiet. We would be hearing the voice of the dead, a signal from a civilization that no longer exists, with no one left on the other end to receive our reply. The light from distant stars that we see in the night sky is already ancient. Some of it left its source before humans walked the earth. In the same way, any signal we might detect would be a relic of the past, a fossil of communication, telling us only that someone was there, once, long ago. This is the cruel arithmetic of cosmic communication. The distances are so great that even messages traveling at the ultimate speed limit arrive as echoes from history, never as living voices. We could fill the galaxy with conversation, and still no 2 civilizations might ever truly speak to one another in real time. The void does not only separate bodies, it separates moments. It ensures that even our words, the fastest thing we can send, arrive too late to matter. There is another sobering dimension to all of this, one that has to do with the nature of detection itself. Even if a civilization existed near enough and at the right time, and even if they were broadcasting signals into space, finding those signals would be like searching for a single specific whisper in a roaring crowd that fills the entire sky. The galaxy is vast, and a signal grows weaker the farther it travels. A radio broadcast spreads out as it journeys through space, its energy spilling across an ever larger volume, until by the time it has crossed many light years, it has faded to a whisper so faint that detecting it requires instruments of extraordinary sensitivity, pointed in exactly the right direction, tuned to exactly the right frequency, at exactly the right moment. Think about how many things must align. You must be looking at the right star, out of hundreds of billions. You must be listening at the right frequency, out of an enormous range of possibilities. You must be listening at the right time, during the brief window when the signal happens to be passing through. And the signal must be strong enough to stand out against the natural radio noise that fills the universe. The odds of all these conditions aligning, by chance, are staggeringly small. Our own civilization has been broadcasting radio signals for only about a century, and those signals have spread out into a bubble around our solar system that, on the scale of the galaxy, is almost vanishingly small. If another civilization wanted to detect us, they would have to be within that thin bubble, looking directly at us, at exactly the right moment, with the right equipment. The chances are remote in the extreme, and the same is true in reverse for any civilization we might hope to detect. This is part of why the silence we hear when we listen to the stars may not mean the universe is empty. It may simply mean that the conditions required to catch a signal are so demanding and the windows of opportunity so narrow that even a galaxy full of life would appear silent to us. We are listening, but the cosmos is so vast and the signals so faint and fleeting that hearing anything at all may be nearly impossible. The silence may be a measure not of emptiness, but of distance. There is a poignant way to think about this. For most of human history, we had no way to listen to the stars at all. We have been capable of detecting radio signals from space for less than a single century, an instant in cosmic time. In that brief window, we have swept our telescopes across a tiny fraction of the sky, listening for a tiny range of possible signals, hoping to catch a message that would have to arrive at exactly the right moment to be heard. The chance that, in this fleeting century of listening, a signal from a distant civilization would happen to be passing through our small corner of space, aimed in our direction, at a frequency we were watching, is vanishingly small. It would be like standing on a beach for a single afternoon, scanning the horizon, and hoping to spot a specific ship that might have sailed past at any point across thousands of years. The fact that we have heard nothing does not mean the ocean is empty. It may simply mean we have been watching for too short a time, looking at too small a patch of water, hoping for a coincidence too unlikely to occur. And even this assumes that other civilizations would broadcast at all. A civilization might fall silent for countless reasons, turning to forms of communication that leak no signal into space, or simply choosing not to announce themselves to a universe whose dangers they cannot predict. The radio noise that our own civilization has been pouring into space for a century may itself be a passing phase, fading as we adopt quieter technologies. If that is the pattern everywhere, then every civilization might broadcast loudly for only a brief window before growing quiet, making the chance of two civilizations overhearing each other even more remote. The silence, then, is not proof that we are alone. It is proof of how staggeringly difficult it is to hear another voice across such gulfs of space and time, even when both parties are calling out into the dark. It is worth pausing to consider how truly alien an alien civilization might be, because even this affects the question of contact. When we imagine other intelligent beings, we tend to picture creatures somewhat like ourselves, beings who breathe, who build, who think in ways we might recognize. But there is no guarantee that life elsewhere would resemble us in any way. Life on another world might be built on a completely different chemistry. It might exist on timescales utterly unlike our own, thinking thoughts that take centuries to complete, or living and fading in the blink of an eye. It might inhabit environments we would consider lethal, thriving in the crushing pressure of a deep ocean beneath an icy crust, or in the searing heat near a young star, or in conditions we have not even imagined. If such beings existed, would they even recognize us as alive? Would we recognize them? A civilization that thinks on a time scale of millennia might regard the entire span of human history as a brief, frantic flicker, too fast to bother with. A civilization that lives and thinks in mere moments might rise and fade before we even noticed it was there. The differences in scale, in chemistry, in the very nature of thought, could be so vast that even if two civilizations occupied the same region of space at the same time, they might pass one another by completely unable to perceive or comprehend the other's existence. This adds yet another layer to the impossibility. It is not only that the distances are too great and the energies too vast, it is that even if contact were physically possible, the gulf of understanding between two truly alien minds might be as uncrossable as the gulf of space between their worlds. We assume that intelligence elsewhere would be something we could talk to, something we could relate to. But the universe is under no obligation to produce minds that resemble ours. The other children of the cosmos, if they exist, might be so different from us that meaningful contact would be impossible even if they were standing right beside us. There is something humbling in this realization. We tend to assume that intelligence is a single thing, a universal trait that would manifest in recognizable ways wherever it arose. But intelligence on Earth has taken many forms, even among the creatures we share our planet with. The mind of an octopus, with its distributed nervous system and its alien way of sensing the world, is profoundly different from our own. And that is a creature that shares our oceans, our chemistry, our evolutionary heritage. How much stranger might a mind be that arose on a different world, under a different star, shaped by entirely different pressures and possibilities? Such a mind might not value communication at all. It might not be curious about other worlds. It might experience reality in ways that have no overlap with ours, perceiving dimensions of existence we cannot imagine, while being blind to the things we consider obvious. The assumption that any intelligent species would want to reach out, would think to listen, would even recognize a signal as a signal, is just that, an assumption, born of our own particular way of being. The universe is not obligated to fill itself with minds that resemble ours, that share our desires, that would even know us as kindred if they met us. And so even the dream of contact, the hope that somewhere out there is a being we could talk to, understand, and call a friend across the stars, may rest on a foundation of wishful thinking. The reality, if there is intelligent life elsewhere, may be far stranger and far lonelier. Not minds like ours, separated only by distance, but minds so utterly different that even the concept of meeting, of understanding, of connection, might have no meaning between us. The gulf between worlds may be matched by a gulf between ways of being, and both may be uncrossable. Now imagine, despite all of this, that somewhere a civilization did succeed. Imagine they overcame the energy problem, built a ship that could survive the journey, and pointed it across the void toward a promising star. Even then, they would face a problem of aiming that borders on the absurd. When they looked at their target star through their telescopes, they would be seeing it not as it is, but as it was. The light reaching them having left that star years, decades, or centuries earlier. The star they aimed at would have moved. Stars are not fixed in the sky. They drift, slowly, each one following its own path around the center of the galaxy, moving at speeds of many kilometers per second. Over the centuries of a journey, the target star would travel an enormous distance from where it appeared to be when the voyage began. The travelers would have to aim not at where the star was, but at where it would be when they finally arrived. A calculation requiring extraordinary precision with no room for error across a journey lasting lifetimes. A tiny mistake in aim, a fraction of a degree, would compound over the vast distance into a miss of staggering proportions, sending the ship hurtling past its target and into the empty dark beyond, with no fuel to correct its course and no hope of ever stopping. And the planet they hoped to reach, assuming there was a planet at all, would be a moving target orbiting that moving star, a tiny speck circling a distant light, its exact position impossible to know until they arrived. They would be threading a needle across an ocean of darkness, aiming at a point that was constantly moving, guided only by predictions made centuries before, with everything depending on the accuracy of those ancient calculations. This is the kind of challenge that makes even the most optimistic dreamer pause. It is not enough to build the ship, to power it, to protect it, and to keep something alive aboard it. You must also aim it perfectly, across distances and time spans that make perfect aim almost inconceivable. The void does not just resist travel. It punishes the slightest imprecision with eternal exile in the empty dark. And there is a problem that comes even before aiming, the problem of knowing where to aim at all. For a civilization to send a ship toward Earth, they would first have to know that Earth exists and that it might be worth the journey. But finding a small, rocky planet around a distant star is one of the hardest things in all of astronomy. Planets do not shine with their own light. They are dark, small, and lost in the overwhelming glare of the stars they orbit. Detecting them requires extraordinarily sensitive instruments, and even then, what we learn is frustratingly limited. We might detect that a planet exists, estimate its size, perhaps guess at its temperature. But to know whether it harbors life, whether it is truly worth crossing an ocean of space to reach, would require knowledge far beyond what any telescope can easily provide across such distances. An alien civilization looking at our sun from many light years away might, with great effort, detect that there are planets orbiting it. They might even notice subtle hints in the light filtering through our atmosphere that suggest the presence of life. But they could not know what we know. They could not know our oceans, our forests, our cities, our minds. They would be staring at a faint, distant point of light, trying to decide whether to gamble the resources of their entire civilization on a centuries-long journey toward a world they can barely perceive, on the mere suspicion that something interesting might be there. Would any civilization make such a gamble? Would they pour everything into a voyage of uncertain reward toward a destination they cannot truly see, based on the faintest of hints gathered across an impossible distance? The uncertainty itself becomes another barrier. It is not only that the journey is too hard, too costly, and too long. It is that the traveler could never even be sure the destination was worth reaching until they arrived, by which point it would be far too late to turn back. To launch such a mission would be an act of faith on a scale that staggers the imagination, a bet placed across centuries on the strength of a whisper. And faith, however powerful, cannot manufacture the energy, defeat the distance, or shorten the time. It can only add one more layer of doubt to a journey already burdened with impossibility. Suppose, though, that we set aside every doubt and grant the most generous assumptions. Suppose a civilization built the ship, found the energy, survived the radiation, endured the centuries, aimed perfectly, and arrived at last in orbit around a distant world. The journey would be over, but the ordeal would have only just begun. Because arriving at another world is not the same as being able to live there. A planet that looks promising from across the void, the right size, the right distance from its star, perhaps even hints of an atmosphere, might be utterly hostile to the travelers who finally reach it. Its air might be poison to them. Its gravity might be crushing, or so weak that their bodies, evolved for another world, would slowly fail. Its surface might be scoured by radiation that its weaker magnetic field cannot deflect, or frozen solid, or baked beyond endurance. The chemistry of its life, if it has any, might be incompatible with theirs. Its proteins, its sugars, its very building blocks built on patterns their bodies cannot use, so that nothing on the entire planet would be edible, and every microbe they encountered might be either useless or deadly. The travelers would have crossed an impossible gulf only to find themselves stranded on a shore where they cannot breathe, cannot eat, and cannot survive without sealing themselves inside the same kind of artificial environment they spent centuries trying to escape. To truly settle such a world, they would have to transform it, to reshape its atmosphere, its temperature, its chemistry, across timescales that might themselves stretch to centuries or millennia. This is a task of staggering scale, requiring resources and technology that would have to be carried across the void or built from scratch upon arrival, by a population already exhausted and diminished by the journey. And all of this assumes the planet was even there, and even habitable, when they arrived, a fact they could not have known for certain when they set out, centuries before, staring at a faint smudge of light through their telescopes. The dream of reaching another world tends to end at the moment of arrival, as if simply getting there were the whole of the challenge. But getting there is only the beginning. A traveler who crosses the ocean of space arrives not at a welcoming home, but at an alien shore that owes them nothing, that was not shaped for them, and that may resist their presence at every turn. The universe does not merely make the journey impossible, it ensures that even the destination, should it somehow be reached, offers no guarantee of refuge. There is one more consideration that completes this grim picture. Every world is bound to its star, and every star has a lifetime. A civilization hoping to reach across the stars must do so within the window, when their own world remains habitable. Before their star changes, before their planet's conditions shift, before whatever forces shape the rise and fall of worlds bring their own era to a close. Stars do not burn forever. They brighten slowly over billions of years, and eventually they swell or fade or end in ways that render their planets uninhabitable. A civilization has only a limited span in which to flourish, to develop, and to attempt the impossible journey, before the very world that gave them birth turns against them. And the journey itself, lasting centuries or millennia, would consume a precious portion of that limited window. A civilization might pour everything into a voyage to the stars, only to have their home world change beneath them, while the travelers were still in transit, leaving the survivors with no home to return to and an uncertain refuge ahead. The clock is always running. The window is always closing. And the journey is always too long. Stacked upon every other barrier we have explored, this final pressure, the limited lifetime of worlds and stars, makes the prospect of crossing the void seem not merely difficult, but almost mockingly out of reach. The universe gives life a brief moment to arise, a brief window to reach outward, and a gulf so vast that the window closes long before the gulf can be crossed. So where does this leave us? We have traveled through the great barriers, one by one, and found each more formidable than the last. The sheer distance between stars, so vast that our fastest machines would take millennia to cross even the smallest gap. The crushing demand for energy, which rises toward infinity as you approach the speed of light, placing an unbreakable ceiling on how fast anything with mass can move. The failure of every propulsion method we can imagine to bridge that gap within a reasonable time, no matter how cleverly designed. The lethal environment of interstellar space, filled with radiation and high-speed impacts that grow deadlier the faster you travel. The agonizing length of any journey, stretching across generations of living beings who would never see the start or the end. The terrible possibility that other civilizations are separated from us, not only by space, but by time, rising and fading in cosmic isolation, never overlapping with our brief moment of existence. The exotic loopholes of wormholes and warp drives, which demand materials and energies that may not exist anywhere in reality. The silence of the machines, the absence of any self-replicating probes that should have reached us long ago if they were possible at all. And finally, the expansion of the universe itself, carrying the most distant worlds beyond any possible reach forever. The lifetime of stars and worlds, which gives every civilization only a brief window to attempt the impossible before their own home turns against them. The hostility of any destination, where even a successful arrival offers no guarantee of a place to live. The sheer cost and uncertainty of the endeavor, so immense that no rational civilization might ever choose to attempt it at all. Each of these alone would be a daunting obstacle. Together, they form a fortress so complete that it is difficult to see any gap in its walls. This is why so many scientists, when they look honestly at the numbers, conclude that the distances between civilizations may be effectively uncrossable, not because of a lack of will or imagination, but because the universe is structured in a way that isolates everything within it. We tend to imagine space as a frontier waiting to be explored, a sea of islands separated by water we can sail across with enough effort. But the truth may be closer to this, that each island is its own universe, surrounded not by water but by an emptiness so profound and so vast that no bridge can ever span it. The stars are not destinations. They are mirages, glittering on a horizon we can see but never touch. And yet, there is something worth sitting with in all of this, something that turns the despair into a strange kind of wonder. If it is truly impossible for aliens to ever reach Earth, then the same is true in reverse. We may be just as locked in as they are, just as confined to our small, bright corner of the dark. But within that corner, we have something extraordinary. We have a world teeming with life, a sun that warms us, an atmosphere that shields us, and minds capable of looking up and asking these very questions. Perhaps the great silence of the cosmos is not a tragedy, but a kind of solemn truth, that every spark of life that has ever flickered into being has been precious precisely because it is alone, separated from all the others by an ocean no one can cross. Perhaps the walls that keep us apart are also the walls that make each living world a sanctuary unto itself, a tiny garden of awareness in an indifferent void. We may never shake hands with another civilization. We may never receive a visitor from beyond the stars. The physics may simply forbid it. But in understanding why, in grasping the true scale of the distances, the energies, and the time involved, we come to understand something deeper about our own place in existence. We are not the center of the universe. We are not its purpose. We are a fragile, fleeting presence on a small world, gazing out at a cosmos that may forever keep its other children hidden from us. And rather than diminishing us, that knowledge might do the opposite. It might remind us how rare it is to exist at all, how extraordinary it is to be a piece of the universe that has woken up, looked around, and begun to wonder. Consider what we are. When you strip away everything else, we are arrangements of atoms, the same atoms forged in the hearts of ancient stars, that have somehow come together in a way that allows us to think, to feel, to ask questions about our own origins. The carbon in your body, the oxygen you breathe, the iron in your blood, all of it was created inside stars that lived and passed long before our sun was born. In a very real sense, we are the universe made conscious, the cosmos contemplating itself through the eyes of beings made from its own ancient dust. Think about the strange journey those atoms have taken to become you, forged in the searing cores of stars that lived and faded long before our sun existed, scattered across space when those stars reached their end, gathered again into vast clouds of gas and dust, collapsed into a new star and its planets, and finally, after billions of years, assembled into a living, thinking, being capable of reading the history of the cosmos written in the light of distant stars. You are the end point of a chain of events stretching back nearly to the beginning of time. The same would be true of any other living thing that might exist anywhere in the universe. Each one, a rare and improbable arrangement of ancient matter, briefly awake, briefly aware, before returning to the dust from which it came. And if the barriers between worlds truly are uncrossable, then each of these sparks of awareness burns alone, isolated from all the others, a solitary flame in an immense darkness. There is a kind of terrible beauty in that. Every conscious being that has ever existed, or will ever exist, anywhere in the universe, may be alone in the most fundamental sense, separated from every other by gulfs that cannot be crossed, knowing the others only as possibilities, never as companions. And yet that very isolation makes each one infinitely precious. And if the barriers between worlds truly are uncrossable, then that makes this moment, this awareness, this fragile flame of curiosity, all the more precious. The aliens may never reach Earth. The distances may be too great, the energies too vast, the time too long, and the expanding cosmos too cruel. But for one brief moment, on one small planet, the universe became aware of itself and asked whether it was alone. And whatever the answer turns out to be, the asking itself is a kind of miracle, a light shining out into the dark, even if no one is ever close enough to see it. There is still value in reaching, even if we can never arrive. There is still meaning in sending our signals into the void, in listening for whispers from the stars, in dreaming of journeys we may never take. The act of looking outward, of refusing to accept the silence without first straining to hear, is itself a part of what makes us what we are. We may be confined to our corner of the dark, but we have never stopped pressing our faces against the glass, searching the night for any sign that we are not truly alone. So when you look up tonight at that scattering of distant stars, remember what each one truly represents. Not a neighbor, not a destination, but a fire burning across a gulf so wide that no living thing may ever cross it. And remember too that somewhere, beneath one of those distant fires, another mind may be looking back at our sun, thinking the very same impossible thoughts, wondering as we wonder, reaching as we reach, separated by everything, connected by wonder alone. That may be the closest to contact the universe will ever allow. Two minds on two worlds, gazing across an uncrossable void, each one a small candle of awareness in the endless dark, neither ever knowing for certain that the other is there. And perhaps, in the end, it is enough. Perhaps the wonder itself is the bridge, not a bridge of matter or energy, but a bridge of thought, spanning a distance that no ship could ever cross. For even if we never meet, the simple act of imagining one another, of caring whether the other exists, may be the most that any two civilizations separated by the impossible distances of space could ever share. It is a strange comfort, but a real one. Across all the barriers we have explored, the distance, the energy, the time, the radiation, the silence, the expanding void. One thing alone can travel freely between worlds, and that is the thought of one another. A mind on Earth can imagine a mind on a distant world, can wonder about it, can hope for it, can feel a kinship with it across an emptiness that no ship will ever cross. And perhaps, at this very moment, a mind on that distant world is doing the same, reaching toward us not with engines or signals, but with imagination alone, picturing the beings it will never meet beneath a sun it will never visit. That shared act of wondering, performed across the unbridgeable dark, may be the only contact the universe ever permits. And in a universe that seems so determined to keep its children apart, that quiet, invisible connection, the shared longing to not be alone, may be the most precious thing of all. The stars will keep their distance. The void will keep its silence. But the wonder will remain, burning quietly in every mind that has ever looked up and dared to ask the question. And that, perhaps, is the answer the universe meant for us to find all along.